reschedule, but we'll go ahead and get at it here. So for those of you that don't know me, I recognize a lot of the names in here, but my name's Ethan Smith. I work for GA Larson. I'm based out of Salt Lake City. Also on the call here, we have Keith Wildab. I can't say his last name today. We have Keith and Larry, who are two of our other service advisors. And they'll be monitoring the chat and helping out in there. And
so did you decide yet?
So we're going to make this as an open forum as we can. So if you guys have questions, feel free to unmute yourselves and jump in, or you can post them in the chat function. And Keith and Larry will take questions and or alert me if we need to address something or if I'm missing something. So it's a good idea to have that chat up open if you're on a computer or an iPad. You can pull that up on the side of your screen. For most people, the unmute button is going to be in the bottom left-hand corner of your screen. You just press that and it allows you to speak. I will ask you if you're not actively talking to please put your phone on mute so that we don't have any background noise or echoing as we go about our class. So I've been with GA Larson for 7 years now. I've been doing the field support, tech support role for about 10. Prior to that, I was a service technician. Worked in everything from small residential stuff, grandpa's floor furnace, all the way up to 200-ton process chillers at the oil refineries. So got my hands in a little bit of everything. Did some low temp, some cryo low temp. Don't ever want to go back into that. Restaurant equipment. No, thank you. So I enjoy being on this side of the desk these days and teaching you guys. So we try to do this class once a year. It's just kind of an introduction to heat pumps. I generally do it in the beginning of the heating season, so because that's when guys have the most trouble with heat pumps and discovering what's going on there. So that being said, we'll go ahead and pull my PowerPoint up here, and we'll get to business here. So heat pumps, guys. What's a heat pump? What on earth is a heat pump? Having trouble on this end. Well, it's a good thing we're in class then. We are going to address that today. Let me go about this a different way here. Sorry, I'm having a little computer trouble on this end. So we're gonna go through all of this today, guys, one by one. Talk a little bit about why we're seeing a surge in the heat pump markets the last few years. Why we're seeing more and more of them. We're going to go through getting familiar with everything, how to control them, and then troubleshooting some of the unique items that pertain to heat pumps. This class does assume that you have a fairly good grasp on the refrigeration cycle and how air conditioners work. We're just going to kind of build on that knowledge to make it heat pump friendly in your brain. So what is a heat pump? So this is via our good friend Webster. It's a high temperature vapor compression refrigeration system that can reverse its cycle. So basically in cooling mode, we're used to seeing this. We've got an indoor unit with a coil and a blower, and we take heat from the indoor airflow, reject it through the suction line out to the outdoor unit where we reject it out to the outside. This causes our air coming into the unit to be cooled as it goes into the house. In heating mode, we do exactly the opposite. We're absorbing heat from the outside air, transporting it through the line set into the indoor coil, and we're using that indoor coil to reject heat to the inside space. Okay, so why on earth would we go through the trouble of doing that, guys? first one is operating cost. More and more and more operating cost on a heat pump has gone down and down and down. So I do have a set of formulas I'm happy to send out to you guys, but this is our annual heating and cooling operational cost formulas. This is for every common source of heat. I have gone ahead and done all of the conversions. So if you follow the values listed on the formula, your numbers will come out correctly. So your heat loss is in BTUs. So if you have a heat loss of 86,000 BTUs, you put 86,000 in here. Your heating hours can be found for your local area. AHRI has those listed on their website. And the HSPF comes from your unit data. Dollars per kilowatt hour. Most electric utilities are going to bill in kilowatt hours, so you don't have to do any conversion there. You just need to find out what your dollar per kilowatt hour is. I like to factor in taxes and connection fees into that because that gives you your total annual cost of operation. But if you just put the numbers in as they're listed, you'll come out just fine. I got a couple examples of this later on. Same thing with gas. This one you have to be careful with. A lot of suppliers will bill by the therm. Other suppliers will bill by the decatherm. So if they're billing by the decatherm, just take your decatherms, multiply by 10. That gives you your number of therms. Propane, everyone bills in gallons. Heating oil, everybody bills in gallons, etc. Okay. So if you guys want a copy of that, just shoot me an email after class. Happy to send that out to you. So why would we choose the heating cost? So back to that operating cost, it can cost less than straight resistance heating. So this is an example for Salt Lake City where I live. We have an average heating hours of 2,300 hours per season. So my resistance heating, I have a 50,000 BTU load just to make it easy. We take our formula from that other page, multiply it by 2,300 hours. Then we divide by 3.41 BTUs per watt. And at the time I did this, I was at 8 cents a kilowatt hour. So to heat my house with straight electric would be about $2,600 a year. Okay. If I contrast that with a heat pump from that same set of formulas with an 8.8 HSPF at 8 kilowatts per hour, I come out at less than half of that resistance heating. The thing about heat pumps, guys, is you're almost always going to pay less per BTU per watt than resistance heating. Okay, so could it cost less than propane? Well, let's run the numbers again. So propane heating, plug it into the formula, and we come out to $3,800 a year. So in this case, when propane was $2.7 a gallon, it's cheaper to run straight electric than to run propane. So yeah, absolutely. My heat pump comes out a lot cheaper than propane. A couple years ago when we were having some really harsh winters, I did have areas out here that were charging almost $5 a gallon for propane delivered. So it became real expensive, and heat pumps became really popular that year in the spring. Less than fuel oil costs a lot, $4 a gallon. So it's almost $4,000 a year to use heating oil. Okay. That being said, oh goodness, having lots of fun today. Does it cost less than natural gas? So right now in this country, it depends. And we'll talk about why a little later. But depending on your natural gas rates and depending on your electrical rates, it may be a toss-up. Whether natural gas is going to work better or worse in terms of cost effectiveness. So you have to do the calculations for natural gas for yourself. I have not done them recently. I did them last year for my system, And I have kind of a unique situation. My heat pump is more efficient in terms of dollars per therm when the temperature outside is above 35 degrees. And it's to run the heat pump, it's more efficient above that temperature, and below that temperature, it's more efficient financially to run my natural gas furnace. So I have the controls set up with what's called an economic balance point. And I'll show you how to do that in a little bit here, guys. So natural gas right now in this country is pretty cheap in most places. So it could be a toss-up. It could be blanket statement cheaper to run natural gas. It could be cheaper to run your heat pump. Just depends. So I encourage you guys to do that on your own. So another reason to choose a heat pump that over fossil fuels is people read the news, people see natural gas explosions, propane explosions, fires, things like that. You know, the disreputable technician going out and burning down a house or causing some CO poisoning. You know, so people consider, you know, a heat pump to be extremely safe compared to burning fossil fuels. Now, you and I all know that if the furnace is maintained properly and all that stuff, and done so by reputable people with good education, that running a furnace in a house is, you know, almost perfectly safe. But people are going to see that, and that's going to be a perception for some people that a heat pump is going to be safer than a fossil fuel furnace. More and more, we're also having the clean energy argument. Now, whether your electricity coming into your house is clean or not, or if you're producing your own through solar, wind, hydronic, that can be a factor as well. You know, using clean energy as the clean energy usage becomes more and more popular. More and more people are moving to heat pumps. So there's a lot of different types of heat pumps out there, guys. Most common that we see are air-to-air heat pumps, which means we have an air source heat pump outside, and we have an air-to-air unit inside. We also have water-to-air style heat pumps. We see this a lot with water source heat pumps or geothermal units. We also have commercial buildings that have cooling towers and things of that nature, where we use a water source on the outdoor section, what would be considered the outdoor section, and we use a air-to-air coil on the inside. We also see this a lot with ground source heat pumps, where instead of a condenser outside, you'll have a compressor and water pump on the inside. It pumps water through piping in the ground and pulls heat out of the ground in the winter and puts heat into the ground during the summer. Also, along the same lines are water-to-water heat pumps, or we're actually using water on both sides of the coil, and we're delivering hot water to either air handlers or floors on the inside to cool the space during the winter months, and we may be providing chilled water to air handlers in the summer to cool the space. We see a lot of this in commercial and industrial applications, as well as some residential. Okay. Geothermal heat pumps are a little different beast, where we're actually using natural hot water to run the heat pump. These tend to be highly efficient, but very limited in scope. It kind of depends if you've got that kind of feature nearby. Kind of unique situations there. A lot of these are split systems. Sometimes in the commercial world, you will see a packaged unit or a rooftop based unit that's a heat pump. Sometimes you'll have little in-ceiling heat pumps that are water to water, but they do have a refrigeration circuit in them. And of course, we've got rooftop units that are heat pumps that'll either have an electric backup, no backup, or a gas pack as well to run that heat on a rooftop supplied unit. Then, of course, we have the ubiquitous PTAC unit, and these are most commonly used in hotels. It's that little through the wall unit that will heat and cool the space. We see a lot of heat pumps there as well. Any questions up to this point, guys?
I'm good so far.
Cool. Keith's being a smartass in the chat. Good job. Okay, so heat pump lingo, guys. There's a few terms that we need to be familiar with if we're gonna talk about heat pumps in an intelligent fashion. So let's get some of the vocabulary out of the way here. So EER is a term we use in heat pump specific more commonly, and that's just the energy efficiency ratio. So this is a momentary glimpse of how efficient the unit is rather than the SEER rating, which would be a seasonal energy efficiency ratio over time. And it's just simply BTUs per hour divided by the electrical power in watts. So it's BTUs per watt. Typically used to rate compressor efficiency, PTAC efficiencies. You'll have EERs on them, and then we use EER in some of our capacity calculations and other calculations that we use. COP is a coefficient of performance. This is also a measure of efficiency. It's generally referred to as the cooling or heating capacity of a system in BTUs per hour divided by electrical power. These two kind of go hand in hand, but they're not quite the same. This one is EER at design conditions. COP is the cooling capacity. It's basically the same thing, but it's at any set of conditions that you set. So we'll look at some performance charts in a little bit where we'll be able to calculate COPs at different outdoor temperatures and different indoor temperatures. Okay. SPF is our seasonal performance factor. We don't use this a whole lot anymore. It used to be a big number that we saw a lot, and it's just the average COP of a heat pump for an entire heating season. But it also takes into effect any supplementary heat that you're going to need. HSPF is just heating season performance factor. It's a little more specific. We do see this used these days more, and it's the same thing. It's just over the heating season. Okay, so let's play with COPs for a second. So COP is simply our output BTUs divided by our input wattage and times 3.41. So 3.41 is your conversion from, it's your conversion factor from electrical wattage to BTUs in electric heat. So if you had 1 watt of electric power going into an electric heater, you would get 3.41 BTUs of heat out of that electric heater. And that's just a universal constant. Okay, so if we take an example here, I'm outputting 28,600 BTUs, and I'm using 2940 watts. And we multiply that by 3.41 watts per, or BTUs per watt, and we come out with a COP of 2.85. Okay, what does that really mean? That means if I were to use the same amount of power to run an electric heater, okay, I'm getting 285% more heat out of my unit than I would running straight electric. So this is a comparison of what you're getting out of the unit versus what you would get out of the unit if you did straight electric. So this is you can think of this as a multiplier. You're 2.85 times more efficient than running straight electric heat with that heat pump at that set of conditions. Okay, so the way we do this is we go to the performance charts, and I'll show you where to get this in just a second, guys. But this is a performance chart out of an AHRI performance table. And so we can find out what those capacities are. So let's take an outdoor ambient of, say, 37 degrees. We want to find our total capacity. So how much we can use, how many BTUs we're going to get out of this thing. So this is a, let's see here, 2-ton unit. And at 37 degrees outdoor and a desired indoor temperature of 70, I'm going to get 20,000 and 100 BTUs out of this thing. And I'm going to use, we go over the 70-degree indoor temperature column, I'm going to use 1.7 kilowatts per hour. Okay, so I can take those numbers and populate those into my formula. So there's my 100 BTUs. I take my 1,700 watts. I multiply that by 3.41 BTUs per watt. We find out I get a COP of 3.46. So I'm getting 346% more heat out of this system than if I were to run straight electric, okay, or 3.46 times more heat. Okay, so that's my coefficient of performance. Okay. Any questions about that, guys? So let me show you a little more up-to-date chart. That's a chart's a little out to date. So if you were doing this for a trained piece of equipment, I'll show you how to do that. American Standard is the same way. We're simply going to go to MyLink Drive, and all the major manufacturers have websites that will help you with this. I'm going to go into my product information, my product literature, go to my outdoor units, and we're going to pick a heat pump here. So I have, let's just grab a split system. So we'll grab one of the variable speed heat pumps, and we've got this column over here that says ratings. So that one we were looking at was a 16 SEER. Let's look at a 20 SEER. So there's my 20 SEER 2-ton unit. And we are with a TAM8 air handler. So there's that same system. Okay. And you can come down in here and see there's all those capacities are, there as well. This is cooling. Come down here, we've got that same chart in heating. So if we were to do that formula again, just grab a post-it note here so I can do my math. We're going to come down to 37 degrees outdoor temperature. So there's my data line that I'm going to pay attention to. Right there. We go to 70 degrees indoor. My total BTU output for that unit is going to be 22,300 BTUs per hour. Okay, I need my wattage as that I'm going to consume to do that as well. So I'm going to come over here to my 70-degree indoor temperature, and I get 1.9 kilowatts. So that's 1,910 kilowatts, or that's wattage, excuse me, times that by 3.41. Let me do some math on my end. So grab my calculator. Okay, so we're going to do the 1910 times 3.41. So that's my bottom number, which is 6,513.1. And then we're going to take my 22,300 BTUs per hour, and we're going to divide that by my 6,513.1, and my COP for that system is 3.42. Okay. Now, AHRI does go out and give you some arbitrary numbers. So down here you see it says capacity 47 and COP 47. So that's already calculating your COPs at 47 degrees. But you notice how it's higher at 47 degrees than it was at 37 degrees. So the COP changes based on your conditions. Okay. They also give us a COP at 17 down there as well. So the COP at 17 is 2.5. So generally, as outdoor ambient goes down, your COP is going to go down because the unit becomes less efficient. Okay. So let's go back to the presentation here. Oh, somehow I got wrong slide here. So if we go back to this presentation, let's just quickly do that same COP at 17 degrees. So we had, using that same unit, it does not want to play nice with me today. Using this same unit, if we were to do that COP at 17 degrees, we would say up here we've got 16,300 divided by 1,054 or 540 times 3.41. Anyone getting there faster than me? Do my math. So my bottom number goes 1540 times 3.41 is equal to 5251. So we go 163.00 divided by 5251. And I end up with a COP of 3.1 on this unit. Okay. So you can see the COPs vary greatly depending on what you're using, what efficiency it is, and what your conditions are. Okay. This becomes important a little later, but we need to be able to use these charts to A, determine capacity at outdoor temperature, and B, determine COPs. Okay. Any questions here, guys? Okay, so everybody remember that. We're going to come back to it. So let's talk a little bit about heat pump components. So things that are unique to heat pump installations, guys. We're going to have a reversing valve. We've got to have some way to switch over from heating to cooling. So reversing valves are called a bunch of different things depending on whose equipment you're talking about, where you are in the country. Someone calls a four-way valve, switchover valve, mode control valve, reversing valve. They're all the same thing. They're just a way to switch modes between heat and cooling. Okay. We're also going to have check valves in a heat pump system. We have to be able to ensure the refrigerant is moving in the correct direction. We do that by using check valves. Biflow filter dryers. Biflow filter dryers are a little newer. Prior to that, we would have two different filter dryers that were directional, one in each direction, that had check valves built into them. We also need an accumulator usually to take care of extra refrigerant. So that's going to make a big difference there, having that accumulator. We're also going to have some kind of defrost control. So there's a refrigerant diagram of just a basic unit. We can see some of those features. Mostly this is the reversing valve that I want to talk about. And let's talk about reversing valves. Before we do that, Keith does bring up a good point about ratings. We pull up the ratings on heat pumps, guys, and it does stipify your indoor coil in those ratings. Make sure you're using rated matches, guys. I will strongly recommend that you stay with the brand of the outdoor unit for the brand of indoor coil. Third-party coils ratings may or may not be totally accurate. We see trouble with that. So back to our reversing valve, guys. So inside the reversing valve, we have this little thing we call a clamshell. We've got 3 pipes across the bottom, and that clamshell is built so that it will make a refrigerant passageway between 2 of those pipes at a time. Okay, we've got a pipe that comes into the top. The pipe that comes into the top is almost always the discharge line of the compressor. The pipe that comes out of the middle bottom is almost always the suction line for the compressor. You'll notice that there's some capillary tubes that come off of the top pipe. It's not pictured in this one. There's actually a capillary tube that comes off of here and goes up to this side of the the pilot valve. Okay, we've got a capillary tube off the side of the reversing valve that comes up here, and another one that comes up here. Okay. And the way these valves work is in cooling mode, that little clamshell is going to bridge between the center pipe, which is our suction, and the pipe that comes from our indoor coil. Okay, so refrigerant is moving through our indoor coil, comes into as a vapor, hits that little clamshell, and then shoots it back into the suction line of the compressor. In the heating mode, we're going to move that little clamshell over, and that way it's going to collect refrigerant off of the outdoor coil line and put that into the suction line. Now, the way these things move over is there's a little solenoid up here on what's called a pilot valve. The pilot valve doesn't actually, the solenoid doesn't actually directly control the clamshell in the reversing valve. We could make a solenoid valve that would control that. It'd weigh about 10 pounds. It'd be 240 volt coils and just be super expensive. So what they use is they use a pilot valve. Like I said, there's actually another capillary tube that comes off of the high side discharge of this compressor and comes into this pilot valve. That's not pictured here. But the way this thing works is you'll notice that there are some seals on either side of this clamshell. It rides on an armature here, and it's got seals inside this big valve body. And that discharge line is carrying high pressure gas off the compressor. It comes up and pipes that high pressure gas into this pilot valve, and the pilot valve is built very much like the main reversing valve. It has a clamshell in it, okay, that controls which side of that valve is exposed to the suction side of the system and which side of that valve is exposed to the high side of that system. So a modern valve is going to have a high pressure line into it, and it's got a suction line into it as well. So what this solenoid does is it moves that its internal clamshell back and forth over these three pipes on the bottom. And you'll notice that the two side pipes on that go to the two sides of the reversing valve. So when we want to change modes on this thing, we are just going to take and change the position of that clamshell. Okay, that's going to pump high pressure gas into one side of this. It's going to hit that seal and push on that that valve, and the suction side is going to actually suck the other side of the valve over to the other side of the valve body through the suction line as well. So it's a push-pull motion to move this. When we want to switch modes, we take that clamshell from here and we move it over to here. Okay, so now the clamshell is over here. We're putting high pressure gas into the other side of the pilot valve, and that pushes that valve armature and assembly inside the valve body over, moving our clamshell over. Okay, there are some bleed holes in here. It's perfectly normal. We've got to have those, otherwise we'd blow out the valve body at some point. Okay. But there are also valve seats here that help limit how much bleed through there is. Okay. In the meantime, the high pressure side of the system simply washes over the outside of that clamshell, gets pumped into the condenser, which is now the indoor coil in heating mode, go through our metering device, go through the evaporator, which is our outdoor coil now, and we come up through the clamshell and go back into the suction of the compressor. So this brings up the point that if you are working on a conventional system, you can't always just gauge up to the line sets in these heat pumps, because your line set in the heating mode is all on the high side of the system. Okay, it's just different sides of the condenser. So in order to get a true pressure reading, you need to make sure that you're gauged up to the true suction line and the true high side of the system. So high side's really easy. You can get it a number of different places. Suction line is almost always going to be that center pipe off the bottom of the reversing valve. And most manufacturers will make provisions for you to get onto that pipe. Okay. So here's some other diagrams here, guys, of refrigerant circuits. So this is just what is this? I don't know what this is. This is a split system here, but we've got a reversing valve over here, and you can see that clamshell depicted in the piping diagram. We change modes, that clamshell just moves over a little bit. And we change direction of our refrigerant. Okay, so there's a cutaway of a train or American Standard unit. We can see our reversing valves over here. We've got a biflow filter dryer right here. We now have an outdoor Txv because in the heating mode, this does act as a evaporator. So we're going to need to meter refrigerant into it. We get some extra sensors with this. We get a Txv sensing bulb down here on the true suction line. And you'll notice that we have ports both on the compressor discharge and the true suction line here so that you can get accurate pressure readings regardless of your mode of operation. Yeah. This particular valve is an internally checked Txv, so we don't have a big check valve that goes around it. It's built into the Txv itself. We mentioned accumulators. So a lot of times you'll see an accumulator attached inside the outdoor unit. This is because during the heating mode, we tend to have a lot of excess refrigerant. This is because our outdoor coils are much bigger than our indoor coils. And when we're using that indoor coil as a condenser, we may have excess refrigerant. That accumulator is there to protect the compressor from getting liquid refrigerant back to the compressor. So the inside of an accumulator it's very simple. It's basically just a giant can. If we cut that can open, the port that goes into the compressor is on the left here in this picture and in this picture. So that port is designed so that it picks up gas off the top of the can. It does go down to the bottom of the can. It's got a little oil pickup down at the bottom. It's usually got a screen on it. We've knocked the screen off of this one, so you can see the little hole that's there, but that's the screen on it. So that'll pick up any oil that accumulates into the bottom of the can, and then it draws that back up to the compressor. The inlet side simply dumps into the top of the can. It's got a little splash guard here to keep it from going into the outlet of the accumulator, but it'll accumulate all that extra refrigerant in here as a liquid. It'll boil off into a gas and get sucked back into the compressor. Okay. As a side note, I just broke down a Mitsubishi unit. It was a big 8-head Mitsubishi unit, and that can stood almost 4.5 feet tall for the accumulator in one of those things. Because during certain modes of operation, that thing may have 28 pounds of refrigerant in that system. So in the heating mode, if you're only running one head, it's got to put all the refrigerant somewhere. So it goes into these accumulators here, guys. Okay. We get the reversing valves that we talked about quite a bit. So this is kind of a CAD drawing of a reversing valve. You see all 3 capillary tubes, one on the suction side, one on the high side, and then our 2 pilot tubes that go into either side of the diaphragm. Various different ways of building clamshells. The white stuff, the white material you see in here is a Teflon-based material. So these things are susceptible to heat when you install them. They may have copper bodies, they may have polycarbonate bodies, or they may just make the whole darn clamshell out of Teflon. But either way, you got to be careful of heat on these things when you are installing them. There's a picture of an actual one. You can see the seals on either side, little bleed holes, and we've got our Teflon clamshell that slides back and forth on top of the valve seat right here. And then we've got our pilot valve, our little capillary tubes that go to either side, and then our suction, discharge, and our 2 coil lines. Okay, so there's picture 1 installed. Kind of already saw that though. And this is just a little animation. So in this case, guys, which mode is this thing running in right now? So is this in heat or cooling mode?
Heating.
Yep, this is in heating mode because we are sending hot gas from the compressor to the indoor coil. Now, we want to switch modes. We fire up that pilot valve. We move the pilot valve over, and the whole rig switches. This is usually accompanied by a loud whooshing noise. Also referred to as the whoosh bang. So just one more shot of that, guys. That whole clamshell just slides over on that valve seat. Anybody see some potential problems in the future here? Points of failure? Think about that. We'll talk about that.
Does that clamshell ever fail to switch over? Or
it can, yeah. Well, we'll talk about why a little later, but that's it's definitely one of the modes of failure on these things, is getting the clamshell stuck. Okay. There's various types of reversing valves out there, guys, all shapes and sizes. That's a big mama there. But the ones that are probably the worst to change out are these guys. They're just miserable. When guys go to change these reversing valves out, there's usually an easier way to do it, and I'll go into that when we go into repair, though. But there's all kinds of varieties of them out there. These are at the time that I wrote this class, these were the current valves used in Trane American Standard equipment. Just kind of depended on your tonnage which one you got. But they all operate pretty much the same way. Biflow filter dryers are kind of unique here, guys. This is a cutaway of one that I got a hold of. And you notice that there are check valves on either side of this filter dryer. The reason for that is filter dryers filter from the outside in. So if this were just a single flow filter dryer, we would always have refrigerant moving through in one direction. But because we're going to have refrigerant move through in two directions, we have to make sure somehow that these things always filter from the outside and push out the inside. Otherwise, when we reversed cycle, we would simply take all the junk on the outside that we had filtered out and then push it back into the system when we change directions. So the way these things work is, depending on which side you're coming in, it's always going to go up through this. It's actually got two check valves in here. It's got a little leaf valve, which you can just barely see right here. It's a little spring valve right here. And it's going to allow refrigerant to come up, pass through that passage, go through the outside of the core to the interior of the core, and then open this spring-loaded check valve here and flow out the other side. So just like is pictured there, we've got our little check valves here, and we've got some spring checks on this plate here as well. And so we're always filtering from the outside in. If you by chance install a non-biflow filter dryer onto a heat pump, what will happen is it'll work great in one mode, and in the other mode, you'll stack pressure on one side of the system or the other. It just won't allow anything through because of that check valve. Txvs also, more and more, we're seeing Txvs with built-in check valves. We almost never see an external check valve on a coil anymore. Basically, in the heating mode, it just allows it to bypass the metering portion of the check valve. So it would in the heating mode, if this were an evaporator, instead of refrigerant coming through the valve seat, it's coming from the other direction, and it's allowed to push past that check valve and just flow straight through the Txv without having to pass through a metering passage. So there's a two-way internally checked Txv and a biflow filter dryer. You notice the key component there is that biflow will have the arrow in both directions on that. Previously, you may have seen ball checks on units that didn't have internally checked valves. There would be a bypass pipe. So instead of having internally checked Txv, there would be a pipe that came off, went around the Txv, and then dove back into the line. Inside that line, you would have one of these check valves that had a steel ball in it, and inside a little cage that had a valve seat on one side and then just a screen on the other. And so when refrigerant pushed out on it from this side, it would actually seat in that valve seat. When it pushed on the other side, it would allow that ball to roll back and refrigerant to go around it. Bigger systems, you may actually have spring checks like this that allow refrigerant to move in one direction. When it comes in from the left here, it pushes up against spring pressure and is allowed to flow through. When it comes back the other side, it actually just forces the valve closed harder. Lots of them out there. Other things you guys are going to see unique to heat pump applications are defrost controls. They are many and various, and we'll go into those in depth right after we take a break, guys. So let's, we're actually moving a lot quicker than we need to be. So let's actually take a break here before we dive into defrost controls, because this is going to take a few minutes. So let's actually take 10 minutes break, guys. Let's be back here by my watch at 5 after 5. So take a 10-minute break, go grab something to eat, grab a drink, slap yourself around, go run around the yard so that you can stay awake through the last half of class. We'll come back and talk about defrost controls. If you guys have questions during the break, feel free to post them in chat or speak up, and we'll get that observed. You might, Keith has a good point in the chat. If you guys look at that, talking a little bit about reversing valves and what it would take to actually run a reversing valve off of a solenoid directly. Kind of fun. So let's be back here at 5 after 5, guys. It's a plenum rated gas valve there, guys. Oh yeah, give that rooftop unit just a little extra support. They're sharing power too. Just adds to the R value, right, guys? No, Keith, you can't twin RTUs. Doesn't work. I was told by the contractor that twinned those two RTUs together that what had actually happened is the compressor in one of them had failed and they couldn't get a compressor for 2 weeks. So there was a unused rooftop unit for another portion of the strip mall. They actually pulled it off of its curb, dragged it across the roof, and panned off the evaporator coil in the rooftop unit with the dead compressor, and ducted the unused unit into the return and supplies of that unit that had the dead compressor in it, and ran it that way for 2 weeks until they could get a new compressor for the dead unit and put it back into service. Anyway, anybody have any questions before we get started again? Kind of throwing a lot at you real quick, so if you have questions, now's a good time. Okay, well then we'll go ahead and get started again. So defrost controls, guys, they come in lots of different flavors. I've pulled a couple of the more common ones from the Training American Standard stuff that I typically support and put them in here. This is kind of the older generation of defrost controllers that we saw for a long time in the Training American Standard units. They've kind of evolved a little bit, but you notice they are backwards compatible with no conversions. We've got the same pin out on the plugs, and then we get a couple little different locations of spade terminals. So spade terminals that were there are now on top of this relay, and we get some other stuff going on. Do get some added features with the new boards that we'll kind of go over a little later. And I don't know why I just did that. Sorry about that, guys. So I mislocated a slide here. I apologize. Okay. I apologize. I thought we were going to go into defrost controls right there in depth, but there's several of them out there. Looks like we get more into them in my diagnostic section. I apologize. But a couple of things you'll see on these defrost controls is we'll have our sensor inputs. So we're always going to have an ambient sensor and a coil sensor in the modern defrost controls. So on the old ones, they were down here. New ones, they're pinned right here. It is a little tough to see on these things, but these are actually a set of test terminals that we got with the defrost controls. So there's my test common, and then I can force defrost or force the defrost to terminate by shorting those terminals together. And that will actually force the unit to defrost whether it needs it or not. This comes in handy if you've got an excessively frozen coil, had a roof dripping on it or something like that. You can force it to defrost repeatedly and clear that coil. There's usually sets of jumpers on here. They're tough to see right here. They're right there. They're marked J1, J2. Sometimes there's a J3. Clipping these jumpers will give you different termination temperatures for your defrost cycle. So humid environments may require a higher termination than a non-humid environment. Depending on your climate or installation circumstance, you may need to clip those jumpers to change your termination temperature. The old generation of boards didn't afford us that always, so that's kind of a nice new feature. And then of course we get a version number on these things. So we'll go into that a little bit. So successful heat pump installations rely on a number of different things, guys. First of them is you've got to have an accurate heat loss or heat gain calculation in order for these things. And so if you don't have that, your system's not going to work in cooling, and it's going to have the added feature of not working even worse in heating mode. You've got to size the system capacity typically to the cooling load was the rule of thumb. Now with the advent of variable speed outdoor units, a lot of times we get better heating BTU output out of them than cooling BTU output. And so we're actually going to size them to the heat pump in the heating capacity of the unit, depending on which style unit you have. So you have to be aware of which equipment you're going to use. If it's going to be a frequency driven compressor, you're going to size it one way. If it's going to be a standard system, you're going to size it in another way. So be aware of the equipment you're going to use. We only oversize to a maximum of 25%. That is assuming, of course, that the ductwork will handle that oversize. Again, ductwork, guys. If you thought airflow was important in air conditioning, it's doubly so in heat pump operations. You're going to have serious problems. Oversizing systems will lower system balance points if you're going to use the system balance point. To control the system. So be aware of that. So on that note, let's talk about balance points. So there's three types of balance points. There's a capacity balance point, there's a supplemental heat balance point, and this can be broken down into staging balance points as well, or there's a system economic balance point. They all operate different ways and achieve different things. So let's talk about capacity balance point. So we've got two lines here. We've got our heating need line in red and our heat pump capacity in blue. You'll notice as the temperature outside on the bottom here goes down, our heating needs go up, and our heat pump capacity as the temperature goes down as well. So where those two lines cross at that outdoor temperature, my system is in perfect balance. I'm providing just enough heat for the house demand for that outdoor temperature. Okay, so I'm in perfect balance. Anytime I'm above that outdoor temperature, my heat pump is a little oversized. Anytime I'm below that temperature, my heat pump is not going to meet my heating need. Okay, so we can use a balance point like this to determine when I'm going to switch over to supplemental or auxiliary heat systems. So we know below 37 degrees on this system, I'm going to have to use supplemental heat of some variety, and above 37 degrees, I don't need any supplemental heat. So we can use that as a capacity heat balance point. So knowing that balance point, so there's my capacity balance point. We can look at the performance of the system and determine whether we want to bring supplemental heat on at that balance point or when we want to bring supplemental heat on at that at various stages. So at 10 degrees outdoor temperature, my system, my house requires 57,500 BTUs of heat. Okay. So if I were to shut my heat pump off at that capacity balance point and provide all the heat I needed, that 5750 BTUs, I would need 16.8 kilowatts of heat to make 57,500 BTUs per hour. We can calculate that by simply taking our BTUs that we require, dividing it by 3 3.413. That number should be familiar because that's 3.413 BTUs per watt multiplied by 1,000 to make it kilowatts. And that will tell us how many kW of electric heat we need in order to generate 57,500 BTUs per hour of heating with auxiliary electric heat. Okay, so this helps us size. Or what we can do is do a supplemental heat balance point instead of replacing 100% of the unit at 10 degrees. So we know that below whatever this temperature is, we'll call it 37, we need to add heat. But maybe we keep the heat pump running instead of shutting it off completely. And so what we would do then is we know that at 10 degrees outdoor temperature, by our performance charts that we looked at before, we know that this heat pump will generate 21,000 BTUs of electric heat. And so all we do is we take the difference between our heating requirement and what we're able to deliver, and we can say, okay, I need 36,500 BTUs per hour additional to my heat pump. And then I can size electric heat off of that, okay? And knowing that, I can actually break my electric heat down into stages so that I don't have to wait until the outdoor temperature gets to 10 degrees in order to bring my electric heat on. I can actually put up to 3 stages of electric heat in there. So I know my unit capacity is here. I can put my first balance point at 22 degrees. So I know when the outdoor temperature is at 22, I'm going to need auxiliary heat because I'm below my system capacity balance point. So at 22 degrees, I may bring in a first stage of electric heat. At 13 degrees, I may bring in a second stage of electric heat. And then at 4 degrees, I may bring in my third stage of electric heat. Now, if my minimum design temperature is at 10 degrees outside, I may or may not need that third stage, okay? But as we saw in this slide back here before, each of my stages in this case, went too far, is 19,000 BTUs. So how many watts is that, guys? How many kW is that heater? First one to get it wins. Maybe if you can get it before me, you win. Anybody? How many kW of electric heat do you need to generate 19,000 BTUs per hour? So we can find out if we simply take that number and we divide it by 3,041 or 3,410 BTUs or per watt. That will give us about 5 kW. So this would be bringing 3 5 kW heaters in, total of a 15 kW of electric heater with all 3 stages running would give us those 19,000 BTUs of heat. So good rule of thumb is 5 kW is about 19,000 BTUs of heat. That changes with your voltage a little bit, but typically 5 kW is going to give you 19,000 BTUs. Okay. So traditionally, this is the way we did it a while back, is we would stage in our electric heat based on outdoor temperature. This required a lot of controls, required an outdoor temperature sensor that had up to 3 different set points. Sometimes it was a giant metal box. You'll still see these things out there on some of these older heat pumps. And it was an outdoor, what they called an outdoor reset switch. And there was up to 3 different temperature thermistors with relays that would stage in the electric heat when we hit certain balance points outside. Okay, so you may see this out here. We don't typically do this a whole lot anymore mechanically like we used to. It's all brought into the digital age with our modern controls, but we can do the same thing. So let's talk a little bit about controls. So we're going to talk about what your low voltage wiring is. We're going to talk about restricted mode and unrestricted mode operations. Okay, so these are some of the controls that we had out there. These have unfortunately all gone away as Trane and American Standard have moved away from Honeywell platforms and into the White Rogers platforms. So this little kit here, this Txvs 103, is that old mechanical dual fuel kit that was out there. We still see these things out there. I had a contractor that was installing them as recently as 2 years ago. So that's that mechanical switchover. Now we're getting into the communicating controls and the solid state controls. It's all different. But if you're going to run a 24 volt heat pump system, I would recommend you get a roll of 8 to 10 strand wire. Find a color scheme that works for you and stick to it. Always use the same colors for the same things. Write it down. Give it to your installers. Keep a copy in your truck. The electricity doesn't care what color the wire is, but it'll make your life a lot easier if everybody on your crews are using the same wiring color code for your heat pumps. Read the instructions, guys. It's not just an e-pad, it is an instruction booklet. Pull it out, make sure you're looking at them. I will tell you guys, if you don't know how to wire a heat pump, the best place to look is not in the furnace, it's not in the heat pump, it's in the thermostat wiring diagrams typically, because it brings it all together in those. If you are running an outdoor sensor, it must be run in a separate cable. If you run your outdoor sensor in the same cable as your control wires, the electromagnetic flux that you get off of those control wires will induce voltage into that sensor wire and cause your outdoor unit or your outdoor temperature sensor to read high or low, depending on whether you are energized or de-energized outside. I have a number of situations that I've run into over the years whereas the outdoor temperature reads correctly as long as the heat pump isn't running. Once the heat pump starts up, outdoor temperature skyrockets or plummets, or whatever is the case may be, and it's all because we're running that sensor in the same cable. So make sure you're running a separate cable for outdoor temperature sensors. Okay, so there's an example of one of these wiring diagrams for a heat pump. This came out of the thermostat wiring diagram. It's typically, like I said, the best place to go. You'll notice a couple unique things. We've got our furnace, we've got our outdoor unit, and we've got our thermostat subbase. Your O terminal is going to come off the thermostat. A lot of times it will land in the furnace, especially in the variable speed models, because that furnace wants to know whether it's heating or cooling, and then it will proceed to the outdoor unit. R, Y, sometimes we'll have a common here. We've got our common wire over on the right. One thing you'll notice is there's usually a black wire in the outdoor unit that is wired into the heating system. That wire is our defrost signal. When the outdoor unit fires, we want to bring the electric heat on so that when we go into defrost, that does not cause the unit to cool off the house. We want to bring the supplemental heat on so that the cooling effect that's generated off of a defrost cycle won't cool the house down. We're going to use that supplemental heat to heat that air back up before it goes into the house. If you don't do this, your homeowners will get a nasty surprise. Every time the unit goes into heat, they'll get a blast of cold air out of the ductwork and it'll be pretty miserable. And you guys will get a phone call. There is a brown wire in some of the older units. That brown wire is typically unused in modern controls. That brown wire was there to signal an error light on the thermostat. Almost nobody has that anymore, so we don't use it. And I believe brown's actually been abandoned in all of the non-communicating units. In the communicating units, brown is now data, typically. So there would be a multi-stage outdoor unit where we've got Y1 and Y2. And then, of course, O, common, defrost, our black wire is going into our W terminals for defrost, things like that. Lots of different ways to do. Okay, other things to consider when you guys are installing or servicing heat pumps. Some of you may have noticed that my heat pump in the background on all these pictures is sitting on a slab. That's kind of a no-no, so we'll talk about that. But if possible, we don't want to locate the outdoor unit on the north side of a building. These things are made to extract heat from the outdoor conditions. And if they're on the north side of the building, that's usually the coldest side of the building. Okay. The other big thing we see with heat pumps, guys, is don't put them outside bedroom windows. Don't put them anywhere where the noise of the unit's going to be objectionable. The colder it gets outside, the louder your heat pump's going to sound. When these things go into defrost, they generally make a lot of noise. So we definitely don't want to be putting them outside the master bedroom window next to their bed. I actually have an installation that I visit almost yearly for a contractor where they've installed these things right outside the master bedroom, and the homeowner is convinced, has to be reconvinced every year that there's nothing wrong with the unit because it made this whoosh banging noise in the middle of the night and woke him up. So,
would you recommend just running a long line set on the outside of the house rather than having to deal with the location?
Yeah, I would. I would much rather have a longer line set than to have a noise complaint.
And do you know about how existential the energy, like having 25 feet of line set on the outside of a house would ever be in any of these cases?
If it's properly insulated, your BTU loss over less than 60 feet is negligible. Typically, if your line sets are sized properly, you may lose 100, 200 BTUs and something like that. If you have a particular instance in mind, I do have a program that helps me calculate those exactly. But typically, horizontal line sets, as long as you insulate them properly, you're not going to have a whole lot of capacity loss. One thing that is unique about heat pumps, when you are running that line set through unconditioned space or on the outside of a building in some line height or something like that, strongly recommended that you insulate your liquid line. Good question.
All right. Yeah, thank you. I appreciate it. We were kind of wondering between us about how much it would actually, go into the affect the system if you had some pretty extreme hot or cold conditions or sitting in the sun maybe.
Yeah. Sitting in the sun for a heat pump's pretty good. I run a heat pump on my house. I've actually got it set up on the southwest corner of my house so that I'm able to take advantage of that warmer ambient temperature during the winter months. It costs me a little bit on my cooling performance, but my system's a little oversized for my house because I do have a variable speed outdoor unit, so I sized it to the heating load rather than the cooling load. But yeah, I would much rather take a longer line set and take a couple hundred BTUs hit on my capacity versus having a noise problem. We got to locate our outdoor units above frost or snow line. If you don't accumulate snow in your particular location, I still don't want to see them on the ground. I'd still rather you have at least a spacer underneath the unit, an isolation pad or something like that, just for drainage. These things do produce water when they're in defrost. If you don't have that pad elevated ever so slightly, you'll get water that'll accumulate in the bottom of the drain pan, and if it's cold enough, it will actually frost up the outside of the coils. That ice will build up on the outside of the unit, and once that coil is encased in ice, the next time it goes into defrost and then goes back into proper operation, it'll generate a little bit of water on the inside of that evaporator, on the inside of that ice shell, and then it'll refreeze that, and then over time it will actually hydraulically collapse the tubing in that outdoor coil. So we see this a lot with Mitsubishi units that aren't put on stands, especially. I have seen it in some other DX coils and unitary systems where we'll actually take that tubing and we actually collapse it, and it goes from a round shape into something that looks a little bit like a crescent moon. And it's shocking what that ice will do to the system. So even if you're in a place where you don't accumulate snow, we still need to be elevated for drainage. They've also got to be level for drainage, guys. That's an extreme case. That's up in Eagle, Colorado. You guys get a lot of snow. He's got a metal roof on it, so he didn't want it to get hit by the stuff. I'm told that the line sets actually go through the column into the house. So be kind of a booger to service, but props for getting above snow level, right? Okay. We do have heat pump legs. They actually just revised these. They've made them out of a different material that's a little more impact resistant. And they no longer have the extensions. They just come in 6-inch and I believe 12-inch or 10-inch versions now. These are actually made to snap into the bottom of the base pan on the Trane and American Standard units. All the other manufacturers have a similar solution. For a while, Lennox there was just having you buy 4-inch PVC, and they had a socket on the bottom of the condenser that you pushed it into. So lots of different things. Mine actually has I made my own out of some 3-inch PVC and a toilet flange, so it's got a nice wide base. Looks kind of ghetto, but it does the job. I had a little unique installation where my pad is not level and it cannot be made level. So I cut my own legs to make the thing level, but to get it above snow level. Okay. Any questions, guys, up to this point? I know we went over the wiring pretty quick. Any questions about that or outdoor sensors or anything? Okay. So other things we got to consider, guys, is like I said earlier, air side. We've got to have adequate ductwork on these things. If you don't have adequate ductwork to run an air conditioner, it's going to be even worse than a heat pump. So we've got to pay a lot more better attention when we are doing air distributions. The other thing we have to worry about in the ductwork is we want to make sure that our outlets are positioned in such a way that we're not going to blow air directly onto people typically. Okay. Heat pumps have a lot lower discharge air temperature than a furnace typically, and so that even though it is blowing air out that's heated, just the simple fact that that air is moving over an individual can be perceived as a cold draft. This is especially a problem with people who've never had heat pumps before and aren't familiar with how they work. So you may need to do some customer education in these situations. Okay. So doing that little bit of education for the customer will save you a lot of headaches back on the back end. Okay. Letting them know what a defrost system looks like. When I was installing these things, I would ask the homeowner if they had ever had a heat pump when I was done doing the installation. If they hadn't, I'd take them out there and I'd do a forced defrost on the outdoor unit so they knew what it sounded like. Show them that, yes, steam comes off of this thing in the winter at various times. I more than once have gone on a service call that said there was smoke coming out of my outdoor unit when it was just in a defrost cycle and they were getting some steam off of it as it ran. So a little bit of education goes a long way for the homeowner and you. Okay, line sets, guys. Size according to standard line set procedures. If you guys ever have any questions about if your line set is adequate or not, please feel free to drop me a line. I regularly size line sets for guys, looking at those long line sets or oversized lines that are there existing, seeing if we need to change anything. It's much easier to fix on the front end than it is after you've installed, guys. So reach out if you have any questions about that. No suction or liquid line dryers in the line set. This is especially true of mini splits. If you do have, the liquid line dryers are acceptable in most cases. The reason I have this in here is I don't want it in the outdoor section. I don't want those liquid line dryers outside. It's much better if you can put those on the indoor section of the line set right before the indoor coil. That way they don't interfere quite as much and don't act as heat sinks in the heating mode. We don't use solenoid valves anymore, guys. Make sure your solenoid valves are gone. all the coils, both indoor and outdoor these days, are integrally trapped. So we don't need solenoid valves to prevent migrations in heat pump systems. Okay. Other things to consider is your electrical service. Your heat pump is going to have a higher electrical requirement than your equivalent air conditioner. That's because we've got extra controls. We generally have a sump heater in the outdoor unit, and make sure that your electrical service is up to snuff. On indoor units, if you're running electric heat, you need to make sure that you have electrical service that will satisfy both the air handler requirement and the electric heat requirement. Very frequently, this requires separate electrical services for the air handler and the electric heat. So make sure you've got all that there as the need may be. Typically, the air handler requirements are going to be pretty low, 10 to 15 amps. And supplemental heaters may range from 20 to 70 amps. So make sure that you've got enough electricity there and that you've got enough services there for your application. Kind of talked about control wires again, but make your life easy, guys. Run some 8-strand to the outdoor unit if it's not a communicating outdoor heat pump, just to make your life easy. You don't want to be running 4-strand or two or even 3 strands of 4-strand, because then you got multiple wires of the same color. I actually have a unit on my shop where I've got 3 strands of 8 conductor run to it. We had to do that because of some experimental controls that the factory was trying out on that unit. And boy, I'll tell you guys, it's sure a nightmare to have multiple of the same color at the outdoor unit. Just make your life easy, guys. If you've got the option, run a spool of 8-strand out there. Keep your life simple. To the thermostat, you may have anywhere from 6 to 8 plus 2 in a separate conductor if you've got an outdoor sensor. Any questions, guys?
Can that outdoor wire be ran next to the other wire?
Yes, it can. The reason it picks up interference if it's in the same bundle is those wires are twisted together. So they're right next to each other and sandwiched in and nested in, so they pick up the EMF. But I mean, even just sitting right next to each other, there's enough separation there that it's not going to be a problem. I wouldn't recommend zip tying them to each other, but yeah, if you want to run a separate wire just along with the line set, what I would recommend is just put a gap between them when you're taping them to the line set. Works fine.
All right, cool, thank you.
Any others? Cool. So let's talk about hybrid systems. When we talk about hybrid systems, the perception these days is that a hybrid is going to be what, guys? What do homeowners think when you start talking about hybrids?
Probably more efficient.
More efficient, yeah. Got hybrid cars and hybrid power systems and all sorts of stuff coming out, and they're all geared towards efficiency. So they are expecting lower utility bills. Okay. So now we talk about a different kind of balance point. We talk about the economic balance points. So this is how I'm currently running my system because I'm cheap, and I don't like paying money.
You mean smart?
What's that?
You mean smart?
No, cheap. Because honestly, I'm more comfortable just running my heat pump into the ground, into the sub-freezing temperatures, but it's not technically the cheapest way to run my heating system. So I'm going to show you guys how to hit that economic balance point. So we do that using something we call a break-even COP. So we talked about COPs earlier, that coefficient of performance, where we can determine how efficiently our outdoor unit is producing heat at different outdoor temperatures. So the break-even COP is simply the COP point where the cost of the operating the heat pump matches the cost of our alternate fuel system. Okay, so it varies greatly. You generally have to recalculate this every year. My customers that we were operating on an economic balance point, what my company would do is we'd sit down at the beginning of the year, figure out what our utility rates were for all our various customers, whether they were on propane, natural gas. And we just have a chart for us for what those were, and then we'd put down some COPs for typical systems that we had, and then we always had the option to look up something if we needed to modify those break-even balance points, because it changed year to year. These are the formulas for that, guys. So natural gas, we've got a constant of 293. We multiply that by the efficiency of the furnace. So this would be 96.8 or 92 or 85 or whatever the efficiency level of your furnace is, just in whole numbers. We multiply that by the price per kilowatt hour. This is in dollars. So if it's 8 cents a kilowatt hour, it's 0.08. And then if we're going to compare that to natural gas, we divide that all by dollars per decatherm. Okay. Same thing with propane. We're going to divide all that by dollars per gallon. Fuel oil, dollars per gallon again. And that will give us a number that is our break-even COP. Okay. So what we have to do with that is we have to take our break-even COP, and then we have to go into our unit and plot some COPs. Okay. So this is that same 16 SEER unit that we were working with before. And so what I've done is I've gone in here and I've calculated my COPs using that formula. And we would just do this every year. Well, the COPs didn't change typically, but we do this for our systems that we installed a lot of. So we had our typical SEER ratings would give us generally the same COPs. So we could go in at the beginning of the year and use our existing COP charts, and we'd have our break-even COPs. So the way you do this is you just calculate a COP for various points on your chart. So we did 2, 7, 12, 17, 22, 27, 32 on this particular one. And we took our output BTUs, which again, we went over to the 70-degree mark for our indoor temperature. At 2 degrees outdoor ambient, this unit's producing 11,600 BTUs, and it's doing it at a cost of 1.4 kilowatts. So we take those numbers, we plug them in for the output BTUs and the input watts, and we get a COP. So at 2 degrees, my COP for this system was 2.41, 7, 2.6, so on and so forth, all the way up to 32 degrees. And you can take this further if you want. With my current system, I actually had to take it up to 40 to find my break-in COP. Okay. What you would then do is take your COP from this calculation and find your outdoor temperature that is closely corresponded to that COP. Then you would use that temperature as your balance point in your control system. So you would set that temperature as your compressor lockout temperature in the modern controls is how we do that. Any questions about that, guys? So just as an example, guys, I did this for my system that's outside my house right now. Right now, with my current gas prices and my current electrical rates, my gas is so darn cheap that back to the beginning of the class where I mentioned that my unit is more economical to run the heat pump above 35 degrees and the gas furnace below 35 degrees. That's how I arrived at that number. I did my break-even COPs for my natural gas and determined that at about 35 degrees, I crossed the threshold from more efficient in my natural gas, more efficient on my heat pump. In years past, when natural gas was significantly more expensive, my break-even COP landed me right around 15 degrees. It's all going to depend on what your utility rates are year to year versus the performance of your particular unit. So be aware of that. One of the things that I do differently on mine is I actually do not use the published AFUE. I actually do a combustion analysis on my systems that I set break-even COPs on, and do a combustion analysis on my particular installation, because that's going to be a lot more accurate than the testing they did in Florida. So that's the break-even COP. Any questions, guys? So back to our heat pumps, guys. Anytime we're either designing, servicing, installing, or doing anything with a heat pump, we kind of have a checklist that we've got to look at. We got to make sure that our heat pump is sized properly, our ductwork is sized properly, our distribution is designed properly. You know, that's more on the installation side or on the pre-installation side, and most important on that side of this of the equation is our equipment selection. You've got to have approved matchups. Previously, you just had to have approved matchups to make sure the darn thing worked. Now you got to have approved matchups legally. The federal government is going to, or has laws on the books now. There's talk of them starting to run random audits on contractors. Not sure how that's going to work out, but basically, if you can't produce an AHRI number for your installation, you're going to have problems. I will tell you, if you don't have approved matchups on heat pumps, you're going to have problems. I'll also warn you that going outside of the brand matchups, using a third-party evaporator or a third-party indoor coil on an OEM outdoor coil sometimes can cause you problems. We here at GA Larson have a particular policy that we do not use third-party heat pump coils on any of our sales anymore. We used to have a line of third-party heat pump compatible coils that we would sell with heat pumps. We found that we had more problems than it was worth, and so we dropped that third-party heat pump coil because occasionally the computer model that generates that heat pump coil matchup for that third-party coil just was not accurate, and it caused problems. But the OEM matchups almost always work flawlessly if they're installed properly. Other things we need to consider, guys: line set sizing. If you're reusing that old line set, make sure it's compatible, especially if they had an AC before. Make sure it's compatible with the heat pump, that you're not going to set yourself up for failure there. The balance point, make sure you're figuring out how your customer wants to control their system. If they're looking for efficiency or if they're just looking to be comfortable. For years, I ran my system on what's called a comfort balance point, which is just a thermostat response. It would track when the heat pump wasn't quite keeping up anymore, and it would periodically bring supplemental heat just as a way to make it comfortable in the house. Works really good, not terribly efficient sometimes. So make sure you know how your homeowner and what they're expecting out of their heat pump, and make sure that you're delivering that. Make sure your supplemental heat is going to be adequate to supply heat to the house, whether you're planning on shutting the heat pump down completely and satisfying all of the heat requirements with the supplemental heat at a certain temperature, or whether you're going to run them concurrently. Make sure that you've got the electrical service both indoors and outdoors in order to satisfy your electrical needs for the heat pump. So just kind of a little checklist, guys. Make sure that you've got everything. There's a little rah for train heat pumps, guys. You know, we've got all the clean energy stuff and no carbon monoxide. They build those compressors to a train spec, and guys, I'm going to tell you, the spine fin coils, man, all that surface area sure makes a difference in the heat pumps. We're able to get more heat out of the outdoor unit than with a traditional plate fin coil, in addition to them having just oodles of surface area that contributes to that. The other advantage of that spine fin coil is when those things go into defrost, they defrost extremely rapidly. I have a 3-ton unit outside. When it does go into defrost, which is rarely, it is usually out of the defrost cycle within 2 minutes because it defrosts so quickly with that spine fin coil. There's literally streams of water that come out of the bottom of my unit when it goes in defrost. It defrosts so rapidly. But there's kind of the raw for those trained American Standard guys that are out there. When we're talking about these hybrid systems, guys, this is what is also referred to in the industry as dual fuel. A lot of times, and so it means that you're using either propane or natural gas along with the heat pump. Be aware of that. If you're using a furnace as your supplemental heat, you can't run the heat pump and the supplemental heat at the same time, because your indoor coil is downstream of the heat exchanger in those installations. So be aware of that, guys. So make sure you're not putting a 6-ton or a 5-ton heat pump and expecting to be able to replace all of its heat with a 40,000 BTU furnace. It's just not going to happen. In addition to the fact that you wouldn't be able to make airflow. So be aware of that, guys. So let's talk a little bit about service. So we talked a little about the components, how to set them up, and let's talk a little bit about service. So charging a heat pump, guys. Heat pumps are charged similar to air conditioners. We're going to charge them to a subcooling target these days because we're using all Txvs. It is critical that you get that subcooling correct. So you're going to look for that subcooling target on the outdoor unit. I will tell you guys, if you're going to err on the side of anything on that superheat or on that subcooling target, it's usually going to say plus or minus 2 or 3. I would say you err on the minus side of that with heat pumps. I don't go over my subcooling target ever on a heat pump charge when I'm charging and cooling. That being said, it is best to charge the unit in cooling mode when it's above 60 degrees outdoor temperature. The reason for that is charging during heating mode is always a bit of a guess. So heating mode charging procedures on the Train American Standard stuff and most other guys, they'll have a heating performance chart that gives you pressures, but they're almost always going to recommend, if you have to charge during a heating season, you can't get an ambient above 60 degrees, is that you do a weigh-in charge both for the outdoor unit and your line set length and your indoor coil, and then come back in the spring and do a subcooling charge when you're above 60 degrees outdoor. It did work for a company for a while that we actually had tents. We would heat the indoor temperature up with the supplemental heat that was 4 or 5 degrees above where they normally would set it for cooling, and then we would actually, while that was happening, we would actually take a little pop-up temp, put it outside over the outdoor unit, and then we would put a couple electric heaters in there to heat the inside of that tent up, and we would actually do a cooling charge in the middle of February on some of these units, just to avoid the second trip. Okay. Refrigerant side problems with heat pumps. Standard air conditioning troubleshooting is going to apply, guys. Just be aware that if you're in the heating mode, you've got a metering device in the outdoor unit now. It's going to operate the same way as your metering device on an air conditioner. It's going to have that same superheat target. You're going to expect a little different subcoolings typically, but not dramatically different. A couple of exceptions, guys, is you got to be aware of where you're gauging up, especially if you're in heating mode. Make sure that you're getting a true suction reading. Reversing valve troubleshooting we'll talk about, and check valve troubleshooting we'll talk about in just a second. So there's those gauge ports in the train units. You just open up that side panel. The reversing valve is outside the coil, and we've got an alternate port for the suction port. And we've got an alternate port for the high side port. Just by way of for clarity's sake, guys, this port up here should be the same pressure as this port down here because it is the vapor line in heating mode. So that comes straight off the compressor, goes through the reversing valve and out that side, and we've got our vapor pressure port right there. Okay. Liquid line is going to be a little different because that's the return from the indoor coil, and so that pressure and that pressure are going to be different pressures. You're going to have some pressure drop through the indoor coil. That's normal. So my recommendation to guys is always just, if you're in heating mode and it's a heat pump, gauge up at the reversing valve, not at the line set connections. I always love taking that call where I get the panic technician that says, oh, my compressor's dead, I've got the same pressure, and he's gauged up in heating mode outside on the service ports. It's because they're both on the same side of the system. Okay, reversing valve troubleshooting. You got to know what kind of reversing valve you have. The old terms were normal and goofy valves. Normal valves is just what we call an energize and cooling valve these days, guys. Most of the domestic manufacturers energize and cooling. The thing to be aware of, guys, is just make sure that you know which it is. Most of the domestics, like I said, energize and cooling. Some of the overseas units, some of the mini splits will energize and heat. So make sure you know which valve you're talking about. Matthew does mention in the chat about wonders if there's pressure drop in the condenser coil in cooling mode. Yes, there is pressure drop in the condenser coil in the cooling mode. It's pretty negligible, though, compared to the pressure drop in heating mode that you'll have across the indoor coil. The outdoor coil in heating mode, you may only have a couple PSI pressure drop because it is so large. The indoor coil is much smaller, so you may have 15, 20 PSI pressure drop in the heating mode. So good question, though.
All right, thanks.
One of the reasons you need to be able to figure out what kind of valve you've got is you've got to know if it's supposed to be energized in the heating mode or in the cooling mode to diagnose it properly. If you go out there and there's no power to the reversing valve and you condemn the reversing valve, you may have just condemned a good reversing valve because it may be de-energized in heating or it may be de-energized in cooling. So you gotta know what valve you're looking at. Electrical checks on a valve, whether it's getting power or not. If it's getting power, typically on the back of the valve there's a little metal screw. You should be able to magnetize to that with a little steel screwdriver. Amperage into that valve body as well. You can check to see if it's energized or not without having to pull the tabs off. It's usually less than an amp on those little solenoids. Other things on a reversing valve is a mechanical failure. So we talked a little bit. We mentioned that this slide mechanism can get stuck. You do have to have the compressor running in order to do the following tests. Pressure should be close to normal. You got to have a minimum of 50 psi difference between the high and low side to make a valve move back and forth. If you have less than 50 psi difference, you may have a refrigerant leak. That's causing your reversing valve not to move over. So you may need to address that before you do this. Okay. When you reverse cycles on the reversing valve, you can do that simply by applying or taking power away from that reversing valve solenoid. You should get that whoosh bang sound as it changes positions. And that's simply the refrigerant equalizing between the high and low side as that thing moves over. That moves that clamshell over. The most reliable method to diagnose a mechanically stuck reversing valve, assuming that those other conditions have been met, is a temperature test. So your hot gas in to your hot gas out should have virtually no temperature change. Your suction gas in to your suction gas out should have no more than 13-degree temperature rise through the reversing valve. It's always going to have some temperature rise just because of the nature of how the valves are built. It's going to transmit heat into that suction line. But if you've got more than 13 degrees of rise on your suction line through that valve, that means that that seal is either failed or the reversing valve is stuck and it's only partially engaged. And so that's going to cause excessive heat into your suction valve, or it's into your suction line returning to the compressor. So that's the sure way to see that you've got a stuck suction valve. But make sure that it's not any of these before you do that, because I have had guys go out, change reversing valves, and then run into the same problem because either they didn't check it electrically or they simply didn't have enough refrigerant in the system in order to make the thing move. Okay. So changing out reversing valves, they're really hard to braze in and out, guys. What I generally recommend is you get yourself a little stubby pipe cutter, and after you recover the refrigerant, cut the old valve out. Do not try to unbraze it. It's just going to be miserable. And then repipe the new valve in and use repair couplings. So we would actually take these stubs and cut them downstream somewhere where it's easy to get the cutter on and it's easy to weld. It's typically very difficult to weld up at these points. The only point that I would say is pretty safe to unbraze is usually this discharge line, because that's about the only one that you're going to have play on. So you can usually unbraze this one, but these bottom 3 pipes, they're really miserable to get to unbraze at the same time. I've seen all sorts of funny solutions to this, guys with triple-headed torch tips. You can actually buy them now, whether you got multiple tips that you can position to try and unbraze multiple lines at a time. It's a lot easier, guys, to cut the old valve out with a tubing cutter and then get some repair couplings that will slide up over the pipe, put it into position, push the coupling down into place, and then braze it. So that allows you to braze the stubs onto the valve outside of the unit where you're not worried about melting coils or things like that. It also allows you to heat sink these pipes a lot easier when they're outside the unit versus inside the unit. Because remember, these seals in here are made out of Teflon. They've got to have thermal protection when you're brazing on them. So I will usually wrap rags around the base of each pipe. I'll also wrap rags around the body of the reversing valve and use water to keep those cool. Or if you've got some of that cool heat conducting putty, you can actually jam it into all these nooks and crannies and get all that heat away from the valve body when you're welding. One thing I will caution you, however, when you're doing this is don't snap your capillary tubes off or kink your capillary tubes, guys. That's where it can all go badly in a hurry. Okay. If you're going to unsweat it, my advice is to have a fire extinguisher handy. And always, guys, when you're welding, flow inert gas, usually nitrogen, so that you don't have problems with your new valve as well. Regardless of whether you're going to unsweat it or not, you got to flow nitrogen both when you're unsweating and when you're welding in. If you don't, you're going to introduce copper oxide buildups inside the pipes. And I'll tell you where that copper oxide is going to build up, guys, is right in your capillary tubes on your pilot valve. And pretty soon you're back changing another reversing valve because it's contaminated now. So make sure you're flowing nitrogen all the time. Okay, we talked about heat sinking, okay, and flowing nitrogen. So, any questions about reversing valves, guys? Yes, Keith, you can burn 3 holes into the coil at the same time with a triple-headed torch. While you're welding on these things, guys, if it's up against a coil like that, they do make some nice heat dissipation mats, which you can get, those little flame guards. It's a good idea to slip one of those between the coil and the base pan and where you're welding on when you're doing these things. Any other questions about reversing valves, guys? Okay, let's talk a little bit about check valves. So check valves of this kind, of the spring checks, are a little tougher to diagnose than the balls. But the first indication that you've got a check valve that's not working is, depending on which mode you're in, you should either have no temperature drop across the check valve, or you should have a very dramatic temperature drop across the check valve. So if this check valve were in the indoor coil, I would expect there to be a significant temperature change in cooling mode across this valve, but no temperature change across this valve in heating mode. This thing should be wide open in heating mode. If I get temperature drop through the check valve in heating mode, I know that I have a check valve that's not opening all the way. Okay. Same thing with the spring checks. That temperature drop test applies as well. One advantage of these little ball checks that you can do is these balls are made out of steel. So you should be able, these are usually in a vertical position. So you can actually take a magnet, put it on the outside of that housing, and pull the ball left and right, and you'll be able to feel it drag on that ball left and right. And in the vertical position, when you move that magnet away, you'll hear that ball click back down into the bottom. Obviously, you have to do that when the refrigerant isn't flowing, but that's one way to check those valves and make sure that that ball is free and clear. Okay, let's talk about defrost controls here, guys. So there's several different types of defrost controls out there. The old ones were just time initiated. You'll still see these on refrigeration systems for like walk-in boxes, things like that, where it's just simply a timer. It defrosts for X number of minutes every hour or every 2 hours. Okay. We also have time and temperature initiated, where it'll actually take a temperature of your evaporator and determine whether it needs to defrost or whether it can wait another cycle. We also have time, temperature, and pressure initiated. So these are a little more uncommon. We generally don't worry too much about the pressure. And then we have microprocessor controlled units, which take a whole bunch of sensors and determine our need for defrost. This is mostly what we deal with now these days. So almost all defrost controls now are time and temperature initiated and terminated. So not only is it monitoring the coil temperature to determine whether it needs to defrost, it's also going to monitor the coil temperature to determine when it's actually defrosted. The thing we have to keep in mind, guys, is anytime we're in defrost, we are wasting energy to defrost that coil. It's necessary waste, but we don't want to waste any more than we absolutely have to. Okay, so some of the symptoms we may see if our defrost control is not terminating properly or not working properly is an incomplete defrost. So we can have this if our sensors are causing that termination to activate too soon. That can be either a calibration issue where we have the wrong termination temperature set, or it could be that our thermistors are not reading properly. So if there's just too much frost buildup, it can't defrost it. So that would be a component of not having set the termination temperature properly. Undersized heat pumps tend to suffer from this quite a bit. They have excessively long heating cycles, and so we may run into a situation where these things are running nonstop and they're simply not able to keep up, and so they tend to accumulate frost more readily than others. Okay. High humidity environments. Case in point, we've got installations near bodies of water, and they build frost really rapidly. And so you may have to have a termination temperature that's a little higher to combat that excessive frost buildup. I in particular had one here in Utah where we typically don't have humidity problems. We live in a high altitude desert here. But I had a gentleman who put his heat pumps, wanted them nice far away from his master bedroom, so we did that. Unfortunately, he installed a hot tub next to the heat pumps a year later, and his hot tub cover was not that great and put a lot of humidity in the air right near our heat pumps. And so one side of the heat pump would frost much faster than the other side of the heat pump. Unfortunately, it was the side of the heat pump that didn't have the termination sensor on it that frosted quicker. So other times you'll see defrost problems is if the defrost is not working at all. So your terminator may be stuck open. So most of the defrost systems out there will have a maximum defrost time programmed into them. It's usually on the order of like 15 minutes though. So if your if your terminator is stuck open, it may run for up to 15 minutes and then reverse cycle. That's usually due to a faulty sensor. You can also have bad timers where it just never comes out of defrost. Okay. Other cases would be if it's defrosting too frequently. This can show up as a capacity problem where the heat pump's not able to keep up or you're running excessive electric heat. So this could be, again, faulty sensors or timers. So you can use the test modes on these things to determine a lot of this. The sensors are simply thermistors where you have to go in and check the temperature reading that those thermistors are giving you. On all the Train and American Standard units, that's a 10K thermistor that they use universally. You get into other brands, they use 20Ks, or if you're into the ductless mini split systems, who knows? You're going to have to refer to each individual unit to find out, and each individual sensor actually, to figure out what those thermistor resistance values should be at certain temperatures. So don't be afraid of that though, guys. Get in there, test the sensors. 9 times out of 10, if you've got a defrost problem and it's not related to your humidity, it's going to be a bad sensor. So get the charts out, look at the sensors. The way we test the timers and the terminations, another way is we can use these test pins that are on the defrost boards almost universally now. And so we've got our test common. If we short from test common to test, if we short from test common to force defrost, it will force the unit into defrost. Okay. Most defrost boards have a minimum defrost time of 1 minute and a maximum defrost time of 15 minutes. If you find that thing goes into forced defrost and then runs for 15 minutes, you may have a sensor that's not reading properly, or a central control board that's not reading the sensor inputs. So make sure you're testing that. And then of course we've got our termination where we can force the termination of a defrost cycle ourselves. Okay, but that coil sensor's right there. You can stick your probes right into the back of the plug and get a DC voltage reading, or you can unplug it and get a resistance reading to check your thermistor values. Okay, same thing there. We've got a coil and an ambient sensor right there. Okay. Any questions about defrost controls, guys, before we move on? Oh, I know what I forgot to add. So remember, guys, there's these jumpers up here. Refer to the manufacturer's documentation. If you've got that high humidity environment, you need to raise that termination temperature. You're going to clip 1 or 2 of these jumpers depending on what you need to get it into a medium or a high temperature. So most coils will terminate at 47 degrees. They know that coil's well above the freezing point, should be clear of ice. You can, depending on your defrost board, you may be able to change that from 47 to 57 or even 70 degrees on your termination. So if you're accumulating excessive frost, let's see what your termination temperature is if you're in that high humidity environment. Okay. Okay, so Matthew says, when in defrost, how does it not blow cold air inside? That's where that black wire in the outdoor unit that hooks up to the heating system on the indoor comes into play. When that defrost board goes into defrost, it's going to send 24 volts back down that defrost signal wire and bring on your auxiliary heat. So that's going to mitigate that cold air. So it's going to bring on that auxiliary heat while it runs in defrost. You've essentially moved into cooling mode at that point. And so it's going to take that cold air that's coming off the coil and then reheat it as it goes out of the unit. Same thing with a gas furnace. You're going to turn the gas furnace off and achieve that.
Okay. All right, that's what I thought.
So that's why I tell guys, we've got a market in Utah down in the south where they don't install a lot of auxiliary heat because they quote unquote don't need it. That becomes a problem when the thing goes into defrost. So I generally will tell guys, even if you don't think you need any auxiliary heat, at least install a 5 kW heater, just so that you can mitigate that defrost cycle, cold air. And I got another question here that says, are there any temps where it will not go into a defrost test? No, that forced defrost test will force it into defrost regardless of outdoor ambient temperature. If all is well in the world, that defrost cycle should quit after 1 minute. But yeah, forced defrost will always work as long as it's in a heating mode. Any other questions, guys? Okay, let's talk about accumulators real quick. So you may be thinking, what's to diagnose with accumulator? It's just a steel can with some pipes in it. You're absolutely right. But there is a situation where we can have a problem with accumulators. This usually needs to be done if you have a compressor failure. So I will always recommend, if you guys have a compressor failure in a heat pump and you've got an accumulator in there, let's troubleshoot the accumulator. So there's something called a torch test. We're going to do this, like I said, with a dead compressor with no oil. And I used to have a video there. Crap. So let's actually go back to my picture of the accumulator. We'll do it there. So we looked at this accumulator here, guys. And what the job of this accumulator is to keep liquid refrigerant out of the system, or out of the compressor. So it does that by having the inlet of it way up here. Unfortunately, anytime we're pumping refrigerant, we are pumping oil out of the compressor. So we have to have a provision to bring that oil back. So I've got this little bleed hole down here. It's usually got a screen of some sort on it, like you see on the right down here. Occasionally that bleed hole or that screen will get plugged up. Usually this is due to people brazing without nitrogen, or having dirty line sets, or pushing their line sets through sheetrock walls and getting debris and things like that come in. They accumulate in the accumulator and will cause that little tube to plug up. When that happens, all the oil that goes out of the compressor winds up in the accumulator. And so what I'm talking about when we do a torch test is you take a torch and you very slowly draw it up the side of the accumulator just to put some heat into the wall. And then with the back side of your hand, start at the bottom of the accumulator very carefully so you don't burn yourself, and just touch the side of the accumulator where you ran the torch. What you'll find is, in a properly operating accumulator, the temperature will change dramatically after about 2 inches on the bottom of that accumulator. In an accumulator that's got a plugged hole, what you'll notice is that oil level is much higher. And so your accumulator won't have a perceptible heat to it until you get above that oil level. Once you get above that oil level, that accumulator is able to retain the heat in the wall of the accumulator. And you'll notice that accumulator suddenly gets very warm along the path of that torch at the oil level. If your oil level is above a couple inches above the bottom of the accumulator, you'll likely have a plugged screen in the accumulator, and you should be changing that accumulator along with the compressor. This unfortunately happens more than I care to admit. I unfortunately only get involved with it after they've changed the compressor multiple times. So if you've got an accumulator in there and you do a compressor change out, this is another good reason that you should be dumping all the oil out of your old compressor to make sure that you've got oil. Okay. I have gone out to accumulators where they have changed the compressor multiple times and the accumulator is completely full of refrigerant oil because it's got 2 or 3 compressors worth of refrigerant oil in that accumulator at that point. So if you are changing out a unit with an accumulator, always, always, always do an accumulator test. That torch test is the easiest way to do it. You do have to do that test once the system is recovered so that you make sure that you don't have a bunch of liquid refrigerant down in the bottom of that accumulator, but it's a good test to do. You can also use an IR camera. I'm from the old school, guys. What can I tell you? I was trained by the old school. I never had an IR camera when I was in the field. Now those are readily available. That's an excellent point. Saves the back sides of your hands. Any questions tonight, guys? That's actually the end of the class. The accumulator is the last thing we talk about, but I'm here to answer questions if you guys have questions. If you think of anything.
I think that the performance side of stuff is really interesting. It's probably obviously the most important part of everything, but definitely on the low end side of install. That's hard to negotiate with anyone. They're just, you're like, unless you can guarantee that they're for sure saving about $20 a bill or something, like some noticeable amount of money, it's hard to reason with them about how good this technology is.
Yeah, and that's a battle we keep fighting in the industry. More and more people are actually going out and hunting for that though now. So the heat pump market has grown 5 to 10% every year for about the last 5-6 years. When I started this job, almost nobody did heat pumps. I started doing heat pumps right towards the end of my service career. I started recommending them more and more, but now, I mean, we used to stock one heat pump of every size and volume in our warehouses locally here in Salt Lake. Now we stock 4 or 5 of every size and SEER level of heat pumps, just because the demand keeps going up for them. So that is a battle you have to fight, especially with the people that are price driven. Personally, when I run my heat pump the way I'm doing it now with my economic balance point, I save, I've got a really old house with really no insulation in the walls and very poor insulation everywhere else. I save about $130 a month on average in my heating costs going to a variable speed outdoor heat pump, because I only run that natural gas when I have to. And the other times I'm getting anywhere from 2 to 3 times as much heat out of my heat pump per dollar that I would spend on electric heat. But right now my line's right there at 35. So when it goes below 35 outside, gas furnace runs. When it's above 35, I'm saving money with the heat pump. So, but it's hard to make promises like that. You're absolutely right, Lee.
I think that, and with the renewable energy, as long as that keeps being able to grow, it's dang near free energy to heat a home.
Yeah, where I probably see the most heat pumps going in is where people are installing solar on their houses. What else, guys? All right, gentlemen, well, if there's no more questions, that's class. I appreciate you accommodating